predicting equilibrium concentrations. So for any reaction, what are going to be the amounts at equilibrium you're going to have? And just what is equilibrium? But being able to predict this and predict it well is pretty darn important, whether you're trying to grow plants or give someone a dose of medicine or just knowing what's going on in the world. That potato chip picture is kind of gross. I thought they actually sliced them up, but oh, it looks horrible. This, look at that. Anyway, so I guess not. Look at that. Ugh. I guess so. That's from Lay's. I won't tell you. Okay. So how do you know when you're at equilibrium? So I need some help. Vivian and Gabby, come on up. I need your help. Okay. So you guys don't have to answer anything. You just have to do stuff. So come on up here. Are we at equilibrium? So do you see this? Here's a container, reactant A. Here's a container, product B. Are you at equilibrium? There's no real way to tell, because equilibrium is when the amounts aren't changing over time. So we need something to happen here. So I need Gabby. This is her. Remember the rate law? It's the rate constant times the concentrations, right? So the rate, here's her rate constant, the beaker. The concentration is just the amount that's in there, right? And then Vivian, right? Here's her rate constant, okay? So what you guys need to do, just at the same time, dip and then dunk, right? So we're transferring product to reactant, we're transferring reactant to product. So go ahead at the same time. Yeah. Let's dip and dunk. Okay, now hold up your beakers. This is really what's important about equilibrium. Are they transferring equal amounts yet? No. Not even close, right? So if they're not transferring equal amounts, these concentrations of reactants and products are definitely changing. So keep going. You got to keep going. So you don't need to scoop. Just kind of go down, straight down. Yeah, there you go. Okay, now put it in. Now bring it up. How much do you have in your beaker? About 30. And what do you have in yours, Gabby? Around 50. It's getting closer, right? So you can keep. So that's good. Thanks. Here's some paper towels if you want. It's food dye, but so you can't even tell. But the point is sooner or later you're going to be transferring equal amounts, and maybe to get those equal amounts, it might look more like. I'm not sure how it ends up, but if you do it a while, it might end up like this. It doesn't have to be equal amounts. All it is just equal. The amount of product and reactant isn't changing over time. That is equilibrium. So when is equilibrium reached? When the amounts of, well, instead of using the word amounts, let's use concentration. When the concentrations of reactants and products aren't changing. Okay. How about the dynamic part? Equilibria are supposed to be dynamic. What did that mean here? Yeah, they're in motion. You're constantly forming product. You're constantly forming a reactant. It's weird to say you're constantly forming a reactant, but you are. So when they say dynamic, we were actually being pretty darn lazy when we draw reactions and write an arrow, right? We have reactants and we have products. We shouldn't just draw one arrow. We should draw how many arrows? 2. That is dynamic equilibrium. We're too lazy to draw it, but we should. Every time you have a reaction, you should draw a double arrow. You should really draw it. It's happening. Products are forming reactants. Reactants are forming products. You can't stop those things from happening. And equilibrium is reached when the concentrations of reactants and products don't change. Writing equilibrium constant expressions. So this is the first part. When you do reach equilibrium, these concentrations, they're not supposed to change. So if I divide the 2 concentrations out, products over reactants, I'll get a number. And that number is going to be the same all the time because, right, the amounts of products, the amounts of reactants, whatever they are, you're going to reach equilibrium, those concentrations aren't going to change. And it'll be different for different reactions, I'm sure. But that'll just mean you'll have different equilibrium constants. And how do you get it? Just divide products by reactants, right? So this Kc is just the concentration of the products all over the concentration of the reactants. So it's not too complicated of an expression to write, except there are some caveats. There are some tricks to it. Some things you never include in an equilibrium constant expression. Equilibrium constant expressions, never, these KCs, products over reactants, they never include what? Pure, does anybody know? Pure liquids or solids. Their concentrations are fixed. If you have a pure liquid, you have a pure liquid. Water is 55.4 molar. If you have a solid, it's a solid. You can't change its concentration. It is what it is. So how do you recognize these guys in a reaction? Right? A going to B. Let's say A is a pure liquid. How is a liquid represented in a reaction? Yeah, aqueous meant AQ, but that's aqueous. We need to write not AQ, we need to write little l, right? So there's a liquid. How about a solid? An S, subscript S. So if you're going to write the Kc for this reaction, it'd just be 1 over 1. There's nothing you can write. So I don't think we're going to have very many reactions like that. Nothing to work on. So let's try one of these here. So Kc, writing just some practice, Kc has to be products over reactants. Now, CaCl2 is the product, so it has to go up on top. And they want concentration. What do you think they're going to use for concentration units, Sabina? What do you think they're going to use all the time? We have several to pick from, but they like one in particular. I don't know why. Give you a hint. Big M. What does that stand for? Molarity. Now, so you can say molarity or molar. Same thing. What was it? Diana, what was molarity? It was what divided by what? Moles of solid over total liters. So you can write moles per liter too, but big M is the easiest thing to write. So we write big M. Now to represent concentration, what do we do special, Jasmine? We don't just write CaCl2. We write CaCl2 in what? In brackets. Right? So products over reactants. So when you see the brackets, you're supposed to say concentration. So the concentration of calcium chloride divided by the concentration of the reactants. So put all those out. We have calcium, and then we have chloride, and we have chloride. Now this is another case where we're never going to write it this way, because what's a heck of a lot quicker? Put a 2 on the top on the chloride. Right? So in other words, when you write these Kc expressions, what did we call these numbers out front? Stoichiometric coefficients. They're always going to become the what in the Kc expression? The exponents, always. Okay. So go ahead and write B, C, and D, and then we'll go on to the next one. So see if you can, I'll ask you. Write the Kc expression for B, C, and D. And be careful, watch those subscripts. Tegan, how'd you write B? Oh, something changed. Yes. So what do you put on top of the Kc expression? The numerator would be what? Just 1. Right? And then on the bottom would look the same. How about C? Crystal Munoz, what did you write for C? And O2 has to be in brackets. And you can do a couple things here. You can write the little g if you want, but a lot of people don't. You can write the 1 if you don't, but a lot of people don't. And then on the bottom you put CO2 in brackets. How about D as in dog? What did you write for that one? Daisy. Okay, now where'd you put the 2? Superscript, right? Then on the denominator, you put now that minus is important, so you got to have the minus in there. In superscript. And then lastly, that chlorine, right? Okay. So
if it's a gas, it's still
oh, good question. It didn't matter. Gas, aqueous, we don't care. Yep. Yeah, so products over reactants. So liquid, we won't have Br2 liquid up here. But on this side, it's just Br minus. So there's no little L written on them.
So you only write the 1 if it's a liquid on the product side?
I just leave out liquids and solids. I don't even write 1s for them.
Okay.
So if wherever you see a solid and a liquid, you just ignore it.
So what about C? Since we left the O2 because
It's a gas. You only leave out solids and liquids. So since it's a gas, you should write O2.
Oh,
Okay. Yep.
Will it be on the reactant side as well? Could there be liquids and
Oh, yeah.
solids?
Oh, yeah.
Same
So
rules apply?
same rule. So wherever you see little L or little S subscript, just ignore it. It never shows up in KC. Doesn't matter where it is. Doesn't matter how many of them, right? I could have 8 carbon solids. Doesn't matter. It doesn't show up. Let's see. Take a look at this question. I have 8 moles. Here's a reaction. 2A, well, the proper way to read it would be 2 moles of A react with a mole of B to produce 3 moles of C. Okay. Listen to this. 8 moles of A and 6 moles of B are initially present. If 6 moles of C are found at equilibrium, how many moles of A and B are also present at equilibrium? My goodness, right? It sounds like one of those 2 trains leaving at the same time, and then you got to figure out what Joey's doing or something. Okay. There's only one way that I really know how to solve these, and I think the book does it the same way. An ICE table. So either you can make a table with moles in it or concentration. Since they gave us moles, we're going to make a mole table. But that mole table is organized using ICE. ICE is going to be a table that we're going to make under there. So all the, what would I probably stand for? Initial. Okay, so do we have any A initially? We'll put it right here. 8 of them. Okay. Do we have any B initially? 6. Do we have any C initially? No, so we can just put a dash. Or zeros. I like dashes because we'll see it later, probably next class period. But notice how the stoichiometric coefficients didn't matter. Whatever's there initially, that's what you put in there. Okay, the change row. Sorry, C is change. I'm supposed to ask you that. But C is change. Am I losing reactant or gaining reactant? Because I don't have any product. All I have is a lot of reactant. So will I get more reactant as a change, or will I be losing it and forming product? Yeah, you got to lose it to form product, otherwise you're not going to get any. So whenever you're solving for something, don't we just put in x, right? So we don't know how much we're going to lose, but you just call it x, right? And you're losing it though, so let's keep track by making it negative. So this is how it always works. Reactants are always negative x. Products always positive x. And we're almost there. We're almost there. This is the only row where the stoichiometric coefficients matter. Otherwise, you just ignore them. See, if you take a close look at this, A is disappearing twice as fast as B, right? Because it takes 2 A's for every 1 B. So they're not the same rate. Or C. C is being produced 3 times as fast as B reacts. So you need to take those stoichiometric coefficients into account. It's not hard. Just put them right in front of the x. All right. So A is going to be reduced by negative 2x. B by negative x. C, you're going to get produce 3x of it. So that's why you have a positive sign. You're producing it. Make sense so far? So this is the only row where the stoichiometric coefficients matter. E probably stands for equilibrium. These are all of our answers. Our answers. Maybe better to set our equilibrium composition, if you want to use a technical jargon. Our equilibrium composition. So here's where all of our answers are. How do you get it? Just add what you had initially, add it to the change, and put your answer in there. So you'd have 8 plus a negative 2x, or 8 minus 2x. You'd have 6 and a negative x. Well, that's 6 minus x. You'd have 3x plus nothing. Well, that's just 3x. Okay. So even though there's something up here we didn't even use yet, right? Like, see how it says if 6 moles of C are found? We didn't even use that number. Don't use it. When you're making this ice table, only use the initial, right? That's all you need is the initial. And then you stop reading the problem. And then you complete your entire ice table and make it complete and done. Then you go back and try to figure out what x is. Because if you start doing the math inside the ice table, things get ugly and confusing. Okay, so now we go back and look at our ice table. Let's clean this up a little bit. So C, 6 moles of C are found at equilibrium. So what has to equal 6? What has to equal 6? C, yeah, but at equilibrium, this is supposed to be 6, right? 3x has to equal 6. That's what you got to write. So outside of your ice table, I mean, a lot of folks, see what I'm saying? A lot of folks like to write 6 here. But I don't see how to solve x. So I don't like to do that. I like to just, once I'm done making the ice table, then I'll do the math. So 3x has to equal 6. So x has to be 2. Okay. Now, when they ask what? How many moles of A and B are also present at equilibrium? So you can't just write an answer somewhere. You got to make it clear. Moles of A equals. Moles of B equals. Okay. A is 8 minus 2x. C is 6 minus x. Now, you don't probably have to write that part, but 8 minus 2x would be 4. You'd have 4 moles. And 6 minus x would be, 4 again. So I don't think that's going to happen very often where they're the same number. But 6 minus 2. Right? 6 minus 2 would be 4. So here's our answers.
Oh, x equals 2. Okay, sorry.
Okay? So finish the ice table before you move on. Okay. So there we go. Boardwalk, board. Right? Fridays go so much better if you're at the boards. Believe me.
Okay.
Trust the old man.
Okay.
Right? So try it.
On that last one,
Mm-hmm.
so the final would just be x equals 2.
Well, the final answers, they wanted to know the moles of A and B. So my final answer is this right here. 4 moles of A, 4 moles of B. That's your final answer. Okay, let's try this. Try the next one here. Let's get the eraser up here. I have more chalk if you need it.
I was late because my mom was supposed to already be
I didn't even know you were late.
But they got stuck at City, and there's like a huge like trailer like that. Like, I don't know what happened.
Well, you can take the quiz after class if you came in late.
Oh, okay, there was a quiz on the.
Oh, there isn't a quiz. You just turn in the bold words.
Okay, because I have it.
Yeah, that's it. You got it.
All right,
Thank you.
you.
Okay, so let's try this first one.
Wait, I can't erase this?
Yeah, you can erase everything.
That doesn't look like it.
So you guys have room?
What do they call it?
Okay. So notice how this is definitely an ice problem, right? Because they want to know what is the equilibrium composition. Definitely an ice problem. Can you come up here? I can give you a big hunk of chalk.
Oh, there's some.
Oh, here's some.
Oh, that's okay. I got some.
Okay. So, definitely an ice problem.
4. Right.
So this should be a C, right? I-C-E.
Oh, that's easy.
And then put a little dash for this guy to show that you're finishing the initial row, right? Or a 0. Yeah, I like dashes, but you can put 0 instead if you want. Mm-hmm. It's always plus x's and minus x's.
Okay.
And it's a 1, so it has to be plus x.
Okay. But if I put this on this, it's not 0.5. It's just 1.
No, it's just x plus 0. You put x.
X right here.
Mm-hmm.
Okay, then equilibrium, what do I do? Okay, now.
Good. Keep going. Everything looks good to me so far. I'd like to have a little dash up there. Or no, oh, here. So for initially, oh, sorry, what is this? Your initial row.
That's the initial.
Oh, you just, yeah, have the reaction on top of the initial row. It'd be a lot easier to read.
Okay.
But other than that, I see, I think I see what you're doing.
Once I get the
Okay, so once you get your x, oh yeah, then you're done. You have to say, but I wouldn't write this. I would say the moles of this guy equals this. The moles of this guy equals that. The moles of that guy equals that.
Okay.
Otherwise, you'll lose points.
Where do I go from here?
Okay, so now you have to add up this row, add up these two, and get this one. Those two and get this one. Those two and get that one.
So 4 minus 3x, 6 minus
Yep,
3x.
and just x.
I had the dandy calculator.
Mm-hmm. Okay, now in your ice table, remember, in your ice table, don't do the math inside your ice table. So, okay, this is good. You have an x down here. So then x has to be 0.5. So you put now, and the only thing that you're missing is I don't know what your answers are.
Oh.
They're numerically correct, but I don't know 3.5 mole of what? 2 of what, right? So make sure you finish these showing your work really well.
Does present at equilibrium and an equilibrium composition the same thing?
Yeah, it's all the E row.
Okay.
Yeah.
So is this right?
Well, see what the folks around you have. So make sure that you clean up your answers. Make sure that you write something like this, like 3.5 moles of calcium. What is it? 5 moles of phosphate.
Why did you get 3.5?
Oh, did I do my math wrong?
Yeah.
See, I can't see calculator generation. It's horrible.
Okay, I forgive you.
Isn't that horrible? So I guess this is what I'm saying. So you don't lose any points when you're working it out. Make sure you're clear as to what your answers are. Because equilibrium composition means you have to give the amount of everything, all reactants and all products. So make sure you're clear. Okay? So if you got it, try the next one. Otherwise, let me help you out and make sure you're following here. There you go. That's going to be that one. Yep. Mm-hmm. Exactly.
I did that math right?
You need a calculator just as bad as I do. No.
That was
This is so low.
I was right.
Well, do 4 minus 3. 4 minus 3 times 1.5.
Oop, I did that thing
Right.
What? Oh, based on order of operations, it's gonna divide this?
Yep. So you can just plug it all in straight away, and it'll know. Order of operations, that's exactly what they call it.
I like this kind of work. Fun.
And so that's just it?
Yeah. Well, though, Crystal, remember, you'll get points taken off. You got to be clear as to what your answers are. So you have to tell me what the stuff is.
Okay. You have to read the...
Yeah.
Okay, so we have the 2, and this goes right here, right?
Okay. Now remember, though, that's what we were talking about before. Don't put your answers in your ice table. Finish the ice table.
Oh, okay, so then this doesn't go here.
This, nothing plus 2x is 2x.
Oh, okay. So then afterwards we do this.
Now you do this and
Okay.
find your x.
Okay.
Exactly. It's cleaner. So nothing plus 2x is 2x. No, it has to be 2x. Because 2 and 2x are not the same thing, right? So nothing plus 2x is 2x. Then you go back to the question, and they told you one of these. Yeah, the calcium hydroxide. So now you write your math. 0.25 equals 2x. See, if you would have wrote just 2, it wouldn't have made sense.
And then now you solve it.
Now you solve for x, and then you put it in for these guys. You'll have all your answers. Good. Yep. And put a little dash.
Like that?
Yeah, or 0. Yep.
Okay. I can do something.
So 2x has to be 0.25. So what's your x have to be?
0.25.
2x is 0.25. X is going to have to be 0.125. So hopefully you're getting 0.125 for your x for this question.
Got it.
Okay. Yes. Yeah, if you get this one, go on and try 14.44. It has a twist in it.
I mean, I help you, but you're a little strong. You're strong for
What'd you get for that one? 2.375?
Yeah, so then.
Okay. 2.375.
Oh, this is all we're going to learn today?
Well, you're going to try the next one. The next one has a twist.
I can do that. Try the next one. See if you can do it.
This one has a twist to it. So if you're started 44, is this an ice problem? No, it's definitely not, because ice is only for getting equilibrium amounts. They gave you the equilibrium amounts, right? Because they said it's an equilibrium mixture. They gave you the equilibrium amounts. They want to know what Kc is going to be. So we need a game plan. Hmm? Product or react. Write the Kc expression. Exactly. If they want Kc, give them the Kc expression and see if you can figure it out from there. Right? Products over reactants raised to their stoichiometric powers, leaving out solids and liquids.
So it gives us the moles and gives us the liters, so to get the concentration we have to divide it by
There you go. You're going to have to find the concentration of every single one, doing what Crystal said. Divide the moles by the liters for each one of those 3. And then you'll have your answer. You need brackets. You can't write them like that. You have to have brackets.
Sorry, I was not here for the brackets.
Good. Now you got to find, Vivian, the concentration of each one of those. Moles over liters. And then you find Kc.
Wait, can we just put... Is that 0.0126 moles?
So why can't I'm sorry, why can't I do it? Because you need to divide them by the liters, each one by the liters.
Oh, each one?
And then the 230 Celsius is just
Doesn't mean anything. Because T isn't in our equation. Temperature isn't, so we don't care.
Oh, okay. Oh, so...
So you have to find the concentration of each one of these.
Where'd that fourth come that you used?
The volume. Because concentration, these brackets are moles over liters. So you have to divide each of these moles by liters, then put it in, and find Kc.
Oh, because KC is the units of large.
Yep.
So what will our final answer be in?
The units of the final answer, it looks like it should be 1 over big M. But we leave all units off of Kc because of activities. And that's something that you talk about in the next chemistry course, analytical chemistry. So we don't write units on equilibrium constants. So we'll just leave it at that. Just don't write units.
And then we plug those in there and then...
Then you plug them into Kc, and that'll be your answer. I don't know. I don't remember. Chlorine.
It just came to me.
Would you use the final answer?
What?
Well, that's not a final answer.
Oh yeah, I have to... I'm letting my brain take a rest.
It's been doing too many calculations.
So it says, did anybody get an answer for this? Oh, I hear a lot of 39s. I bet that's right then. To keep going, if you got 39, go on to the next one. Okay. Go on to the next one, 55 if you got 39. Otherwise, make sure you can get it on your calculator. Make sure you can get 39 on there. sure you can get 39?
I lost my pen. No.
Vivian, can you get it on your calculator though? You sure? Okay, oh, so you got it. You plugged it in. Okay. Hey, who do you think is going to Huey Lewis and the News and got front row tickets?
Yeah.
10 a.m. they went on sale.
You?
Huey. All right. So everyone's come from 39. So hopefully you're working on 55. All right.
You just have to write
Yeah, just write concentration of products over reactants. What did you do with the 1/2? Yeah, make it a superscript. What does the half mean if it's a superscript? Square root. Yeah, that's what it means. So you pretty much had CO2 all over O2. Oh, I forgot about the SO2, didn't I? Okay. A couple more. Then your weekend can begin.
This one looks simple, but it could be hard. It's already giving you the mole.
Yeah.
So you just do the Kc equals whatever, which is this. Then do you just plug in and if it's squared?
Whoa. Couple things. One, if you were going to do this,
Okay.
you can't because you don't know liters. Right? Because this has to be brackets. This has to be moles over liters. So it's not this type of question. It's just a straightforward ICE one. Read ICE. Right? Yeah, this one right here is what is the composition? Whenever they ask what is the composition or what is the concentration of something at equilibrium, it's going to be an ICE table.
Okay.
It's going to be an ICE table.
And what is it going to be, Casey?
They have to give you moles and liters.
Okay.
Otherwise you can't.
Oh, so because there's no liters.
Well, not really. To me, it's because they want to know the composition. If you ever want to know composition, it has to be an ICE problem. It's not going to be a KC problem. Because that E row is the composition at equilibrium.
The possible -1 thinks that's possible.
Yeah. Yeah. On the reactant side, yeah. Careful. That 0.0311 isn't initial. Right?
So if I just write.
Don't change rules on the ICE table. ICE.
Oh, this we need. We do.
This
need
is an ICE table. Whenever they're asking for equilibrium composition of anything, equilibrium amounts.
I make sure.
He's not initial. Put down ICE and then the initial. No, you're okay. I.
Oh.
There you go. Cause there you go. Man, you don't like to write zeros, do you, Jasmine?
Oh, he was telling me to do that. I didn't.
Oh, that's your dash. Oh, okay.
No, that's the. Like this.
Oh, so you just do 2 times.
Divide by 2.
Yeah, I know. But I'm asking her how she did this.
Because I
But that says what? Yeah, 2x. To get the x by itself, you divide it by 2 here, 2x is 3 divided by 2 here. Just equals 0. Oh, you divide it by 2 because of. Okay, got it. Sorry. That's what I've learned. Tricky man right here, tricky man.
So, Casey, can we just do this?
0.0112. You guys all agree?
ATM.
I got 224. We're off by like tens because I got 224.
Well, she has 0.0155 for your x. And you have 0.015. So you might be off a little bit, but it won't be much. Oh, yeah, I can't subtract 0.0. Oh, 2 times x. That's right. 0.0311. Subtract 0.0311. You're subtract 0.03. She did 0.0311 or something. I don't know. But 0.0214 and yeah, it's because of the 1. She has a 1 here and you don't.
Hey, Dr. Smith, let's
Mhm.
do the last one all together.
Oh man.
The last one?
Leave the
No,
answer.
it's not.
I don't have the answer up.
Yeah, but let's do it together.
Yeah.
Okay.
You gave us one ATM.
So PCl5 has to be 2.5 initial. Okay. Do I have anything else initial? Nope. That's to give. So at 0.38, this phosphorus trichloride has to be that. Yeah, so the 0.338 has to equal the x. You don't have to divide by 2 or anything. So that 1 ATM and that 160 degrees Celsius meant nothing, right? We don't have P in the ice table. We have a pressure. have a good weekend.